So on Friday, I talked about alpha beta search. Today is going to be the second lecture on how to do Project 2, but whereas on Friday I discussed the algorithm, today I'm going to discuss software engineering, and in particular, how to do a group project, how to write a large piece of software with several teammates. And the key to that is called encapsulation. The idea of encapsulation is that you want to, before you even start programming, divide the logical design of your game-playing program into a bunch of modules. What's a module? Basically, a module is something you can wrap a simple interface around. More specifically, it's a set of methods that work together to perform some task some unified task. Like, for instance, to determine whether or not a game board has a winning network. And what defines the module really is the fact that you can put it into a nice encapsulated module that has a cleanly defined simple interface. So a module is said to be encapsulated if its implementation is completely hidden, and it can be accessed only through a documented interface. So these two things together, the hidden implementation and the documented interface, mean that someone can use your module and call your module without having any idea how it works. They know what it does, but they don't know how. So I've discussed encapsulation before, without using that word, as a way of preventing evil tamperers from meddling with your data structures. And who are these evil tamperers? Again, as I said, often they're your coworkers, but quite often the evil tamperer is yourself. And so let me sort of tell a generic story that's happened thousands and thousands of times in Silicon Valley, and probably happens every day, and today included. Let's imagine a programmer named Doug working for a company in Silicon Valley, and his job is to write linked list code for the company's flagship list mangler application. So, well, one day he's sitting coding, and he needs a method that removes the second node from a linked list. Now, this isn't something that comes up very often, wanting to remove the second node from a linked list. So he figures, since he's only going to need to use it once, instead of going back and writing a whole separate method just to remove the second node from a linked list, why not just write one line of code right in his application that does it? Now, maybe he's not working in Java. Maybe he's working in a language like C that's like Java, except you don't have private and protected and package protection. Everything is public. Or maybe he's working in Java, but just he declared everything public. So here he is working on the list mangler class, and he's feeling really lazy, so he just says, okay, I'm just going to remove the second node from the list in one simple line of code. Rather than writing a whole method just to do that, because, you know, he's got a lot of work to do. And this is the easy way out. And there's lots more code there, and so he has a productive day, Doug. 2 years later, another programmer at the same company, let's call her Jeannie, is given the task of taking the company's list mangler application, their biggest seller, and changing it to make it faster. And after inspecting the code, she decides that the way to make it a lot faster is to use doubly linked lists so that she can go backward through the list in constant time instead of linear time in the many cases where that's necessary. So she's retrofitting the S-list class, replacing it all with D-list classes. And so she goes ahead and makes this change, replaces the lists with doubly linked lists, and lo and behold, the list mangler application stops working. It doesn't stop working right away. You know, maybe this line still does the right thing in the short term, but this line of code is not readjusting the prev pointer. So the list gets broken, but the prev pointer maybe isn't needed until some point later in the code, 1,000 lines later, when someone's walking backward through a list. And because the list has been broken by this line of code, the list mangler application crashes. Well, the crash didn't happen at this line of code. The crash happened 1,000 lines later. And the crash didn't happen in the list code itself exactly. Well, I mean, the crash happened in the list code, but the bug was not in the list code. The bug is over here. So this kind of thing happens in the real world every day, and these are the hardest kinds of bugs to find. I'm going to write that down. It's a systematic bug. It's not a local bug. It's one where the problem is far, far away from where it appears to be. So this is just one of the hardest kinds of bugs to find. It's also very common in commercial software systems and can have far-reaching effects. Now, okay, so maybe it takes Jeannie just one hard day of debugging before she finally traces the bug from over here where the prev pointer is wrong back to here where it got mangled in the first place, 1,000 lines of code away. So she finds that and she fixes this one line, but maybe Doug wrote 100 other lines just like this. Maybe Doug was lazy every day and not just one day. In that case, you know, she might discover she has 100 more fixes like that to make and 500 more fixes in other programmers' lines of code that also tampered with the internals of the list class. And so in the end, she has no choice but to abandon the list mangler improvement project. They're stuck with the old code. And again, that's a real story. When software systems get larger and larger, eventually they get to a point where changing them, almost any change, seems to break them. And this has happened. So they say, for instance, that in really large-scale software projects, 1 million lines of code or more, often have failure rates of 50 to 60%, meaning a company commits 20 programmers or more to some project and works on it for years, and in the end, they have nothing to show for it. An example of that was in the news a few years ago was the Denver International Airport's luggage system. Apparently, they never actually got it to work. They had this pristine new airport. Its opening was delayed by 3 months because the fancy new baggage system didn't work, and the fault was they never could fix the program. It was too big, too cumbersome, had too many kludges in it, and just couldn't adapt to the point where it worked. And they had to retrofit the airport with an entirely new and much more primitive baggage handling system before they could open the airport. It cost them millions of dollars. So how do you fight this kind of thing? Well, we've seen some ways of fighting this kind of thing, and that's what encapsulation is all about. If the head variable had been declared private, for instance, then Doug would have never been able to introduce this bug in the first place. And so you want to keep the same things in mind when you're doing your project, and I'll talk about several ways to do that. But the high-level idea is that you want to divide your project into modules. Modules, again, are things that have a very simple interface where you can hide the implementation. And that doesn't necessarily correspond to class boundaries, which is one of the things that makes it a little hard to understand. But you should think of a module as being a box. So here you have a module, or you have an abstract data type, which is a type of module, really. And that module has an interface. It's a very well-defined, non-ambiguous, publicized interface. And the only way to get information in or out of that box is through the interface. So you can send information in and get information out by method calls. And applications that want information about what's in the list must go through that interface. They're just not allowed to do stuff like this. And this in a picture is what encapsulation means. Why do we like encapsulation? There's lots and lots of reasons. First of all, the implementation is independent of what the module does. So if you have the interface documentation, then you should be able to go off into a quiet room and reprogram the whole module yourself without ever knowing how the original version of the module was programmed. Now, the second reason is that if you've done encapsulation well, you can use it to prevent Doug from screwing up your list mangler application. And that reduces debugging time in large applications. And it reduces debugging time a lot. A third one, abstract data types have invariants. Well, encapsulation means that ADTs have the power to ensure that their invariants are enforced. So for instance, if you want to create the invariant that your prev pointers agree with your next pointers, then you can do that in your lists. Now, number 4, which is the one that really pertains to you in the near future, is teamwork. This is how large companies write large programs, is by dividing them into modules so that each person can work on a different module independently without knowing how their teammates are implementing the other modules. The thing you have to do together is you have to define clear interfaces. But once you've got those, you're ready to split up, in a sense, and each do some of your work independently. And so a really large programming project can be broken up into dozens of pieces. And number 5, it gives you good documentation and long-term maintainability. So by having clear interfaces, you make it possible for other programmers to fix bugs that arise years after you've left the company. Most bugs that arise in large systems are a result of unforeseen interactions between modules. If you've clearly defined exactly how your module behaves, then it's a lot less likely that there will be a miscommunication between modules. So kind of my summary of how you think about the design of modules, and in particular the design of interfaces, is that it's a contract. An interface, in this case, you can think of it as a contract between you and your project partners. You're saying, if you write your evaluation function this way, and I write my alpha-beta pruning search that way, when we put them together, they will work together. And we'll have a working game program. And so this contract specifies exactly how our modules will communicate. Any questions on this so far? Yeah. The keyword interface? Not really. I mean, the interface keyword is used as one way of defining interfaces, but you certainly don't need to have a Java interface to define an interface to your module that other people can call. But you can do it that way. Yes? Example of different modules? Well, the simplest example I can come up with off the top of my head is the one that I've already talked about before, where you have an application that has lists of numbers that it needs to sort, and then you have a list sorter. And the interface to the list sorter might just be one single method, something like public void sort list. Let's make it ints, just to make it simple. Some array of ints. So your prototype is half of your interface. Your other half of the interface is a plain English description of what it does, like, for instance, sorts numbers from smallest to largest. So I have a longer example that's in the lecture notes, but I'm not going to have time to write it on the board of what is an example of an interface to the valid network component that you'll have to write in Project 2. So that'll give you a second example, but it'll be in my lecture notes. You'll have to download that. Yes? No, so there is no explicit module keyword, first of all. And second of all, what makes a module hard to define is that it does not fit the constraints of the Java keywords. And for instance, a module might be made up of several classes, or a class might be made up of several modules. And that makes it confusing. So I'm going to talk about that in some detail shortly. Other questions? A few words on how you enforce encapsulation. You already know most of this. Basically, well, first of all, let's not talk about Java, but let's talk about most languages. Most languages give you one construct for enforcing encapsulation. It's not a very powerful one. Self-discipline. Java gives you a little bit more, fortunately. So does C++. C does not. Pascal does not. Lisp does not. Scheme does not, as far as I know. But in Java, we have Java packages. So packages, what they allow us to do is take a bunch of classes that work together, put them into a package, and then those classes can see each other's protected and package protection fields, but those fields are still off access to the general public. And then there are the private package and protected steps of protection that prevent that allow you to define fields that are not public. And that's most of what you've got. This is not always enough. Why is it not always enough? Well, because sometimes you have to put multiple modules in the same package. Why would you want to put multiple modules in the same package? Well, because often you have a bunch of different modules that operate on the same class. So an example of that is in Project 2. It would be perfectly reasonable to put all of your modules in the player package. You don't have to. If you decide to use a linked list, for instance, it would make sense to put that in a separate list package. But most things will go in the player package because most things will go in the game board class. Whatever your representation of a game board is, you're going to be doing things like computing whether the game board has a network. You're going to be doing alpha-beta pruning. You're going to be doing an evaluation function on the boards that you can't search all the way to the bottom. So those are three different operations that you have to do, all on a game board. They can be separate modules because they can be separated from each other in a nice, clean way with nice, clean interfaces. and yet they all belong in the same class because they all operate on the game board data structure. So in that case, you have to fall back on self-discipline once again. So here's another way to improve your self-discipline. When you can't count on private, protected, and packaged to keep you safe, another way to do it is, once you divide your project into modules, is to have a different team member implement each module. Now, if none of the team members reveals their code to each other, at least not in the early stages, then it forces you to hash out an interface that has everything you need so that your module can work with the other person's module without tampering with its internal variables. Now, of course, there does come a point when you want to reveal your code to each other. When you start debugging it at the very latest, you're going to want to do that so you can see where the bugs are coming from. But if you do this in the beginning, then it helps you have good discipline and form really good interfaces. Any questions about that? So that's the general software engineering talk, and now I want to talk about Project 2 specifically, what you need to do. So you are required for Project 2 to divide your programming task up into modules, create well-defined interfaces between them, and document those interfaces in your grader file. That's a file that will be submitted with your project. And we expect you to do that before you start programming. And we expect you to show it to your TAs in next week's lab section so that they can check whether they agree with your design. So how will you break up the project into modules? Well, here's sort of a basic uncontroversial breakdown into at least 4 modules. You've got your machine player at the top, which takes care of general simple tasks like checking whether moves are valid and playing new game pieces and registering the opponent's moves and maintaining the game board. And then you have to decide what moves you're going to make. And to choose a move, you have to do some sort of game tree search. Which I discussed in detail on Friday. Now, game tree search needs several things. First of all, you need to be able to figure out whether somebody has won or lost the game. And for that, you need a network identifier, something that determines whether there is a winning network on the game board. And that's actually a somewhat complicated little algorithm. So you probably want to make that a separate module and have one team member spend a lot of time thinking about how to do this. Another thing you're going to need is, since you can't search all the way to the bottom of the game tree, because it's exponentially large in the depth, and you just can't do the gigantillions of game boards that in the 5 seconds or 10 seconds you're allotted, you're going to need to have an evaluation function and the evaluation function's job is to look at a board and say, is this board, how good do I think this board is? How optimistic am I that I have a better chance of winning than my opponent. And the evaluation function might need to call the network identifier itself. Now, this is not necessarily all of the pieces. The project handout describes a few other possibilities. You might find a way to break it up into 5 or 6 pieces. But on the other hand, a real determinant for whether it's a good idea to break a module up into smaller pieces, into several modules, is how complicated will the interfaces be. You don't want the interfaces to get too complicated. That's a sign that you're breaking things up too much. So maybe break it up a little more than this, but don't break it up too much. You might find something between 4 and 7 pieces that work well. But again, what defines a module is that it's relatively independent of all the other modules and that it can communicate through a relatively simple interface. Simple doesn't necessarily mean short. The interfaces for the D-lists you guys have been writing are not short because there's lots of functions you can call on a D-list. But simple is something that goes by feel. It's if you're passing in parameters that don't make any sense because you need some sort of weird value, you're probably breaking it up too much. Really, knowing how to break things up into modules is something that only comes through experience and practice with programming design. So you'll start getting that practice in this class and continue to get it for as long as you take programming courses here. Any questions on this so far? Okay, so again, you may still be confused. What exactly is a module? Well, let me talk first about why it's confusing before I try to re-clarify. So first of all, a module may include many methods or as few as one. Your game tree search might turn out to be just one big method, maybe. So it's not the number of methods that you have that defines it, although you shouldn't succumb to the temptation to make every method a separate module. Now, one of the things that makes modules confusing is that a module can be made up of several classes. And a class can be made up of several modules. So the divisions between modules do not match the divisions between classes necessarily. And let me give you examples that show each of these two situations so that you can understand why. And you've already seen both examples, actually. So why would a module have several classes? Well, because a module might implement a data structure that needs several classes. So you've been examples of this, the list classes. Any reasonable list class requires, any reasonable list ADT requires at least 2 classes. You need a list class and a list node class. And I've talked in previous lectures about why it's good to have those separate from each other. So there's an example where one module, one logical module, is made up of 2 classes, dlist and dlist node, or maybe more if you throw in a list superclass and a test helper and other classes. the reverse situation where you might ask, why would a class have several modules? Well, the class might be a data structure that supports several independent functions, like your game board. So, for instance, game tree search and your evaluation function. They both operate on the same data structure, a game board. So it just makes sense that they should go into the same class, even though it's very easy to divide them into two separate modules that are independent of each other. And so someone suggested packages, but packages aren't really the right divider either. Because a package can contain one module or many, just like your player package may wind up containing all of these modules. Question? I would say that the ocean class was probably one module, is how I would look at it. Yeah, it's sort of like the list class. It's like one coherent data type that has lots of different ways you can access it. And the run length encoding, maybe you could see that as one abstract data type, but you could certainly separate different parts of it into pieces that different people could implement. So if you've agreed upon what the data structure is for run length encoding, once you've got the data structure pinned down, then one project partner could go implement a run length encoder that converts an ocean to a run length encoding, and someone else could do the reverse, a module that converts a run length encoding back to an ocean, and you wouldn't necessarily have to talk to each other to do that. So what really defines a module is not classes, not the class boundaries, not the package boundaries, but the question of what makes a clean interface. And what makes a clean interface is not the same as what makes you divide something into two different classes, which is needing two different kinds of data structure. And so that's why a list module might need several classes, but you might be able to fit several modules into one game board class. Is because that's where the interfaces are clean. There's no clean interface between lists and list nodes. They work together. Other questions? So for project 2, again, you're being asked to document this stuff. How you split things up into modules, and what the interface for each module is. And so this is an exercise in thinking about how to break up a project into pieces that are independent and can be programmed by different people. So the first thing you have to do is you have to list the modules. Now, hopefully it's obvious by now that listing modules is not the same as listing classes. You have to give your modules names even though those names may not appear in your code anywhere. Like the game tree search module. Once you've made those decisions, then for each module you can specify its interface. And this is how your project partners know how to write code that works with your code. So the interface includes, again, the prototypes for the methods that are available to external callers. And once again, you do not have to document the helper functions or stuff that's only called internally within the same module. Now, for each of these prototypes, you have to describe in plain English how the method should behave. Now you describe the behavior of a module or of a method call from an external point of view, which means, again, you do not have to describe how the method is implemented. You only have to just tell what it does from an outside observer's point of view. So you can say, my game tree search module does game tree search according to the minimax algorithm. Any information about how you implemented that is optional. So if you want to, you can say that you used alpha-beta pruning, but you do not have to document that you used alpha-beta pruning because that's how you implemented the algorithm, and that's not what it does. Alpha-beta pruning does not change the results returned by minimax tree search. It only makes it run faster, and that's not something you have to document unless you want to. Or another example is your network identifier in the project. You have to state that it returns true if there's a network for such and such a color and false if there is not. You don't have to state what algorithm it uses to figure out whether there's a network or not, because you could change that algorithm if you decide that you have a faster way of doing it. And finally, it's generally important that the behavior comment also is explicit about what happens in special cases. So if something goes wrong, if the input data is malformed, how does it react? And it's important that you discuss what every parameter does. List all the parameters and say what they do, and what the return value is, if there is a return value. And how these are interpreted. Because the parameters and the return values are really a contract between you and an application about how you are going to communicate with that application. Now, these descriptions of behavior should be as complete and unambiguous as you can make them. Otherwise, you might have misunderstandings with your project partner that will lead to hard-to-find bugs, because you think the interface is supposed to work one way, they think it's supposed to work a slightly different way, you wind up with the wrong answer. You should generally talk about how you cope with unusual and erroneous inputs, or just weird circumstances that aren't the norm. And sometimes it's okay if your module responds very badly to erroneous input, but that should be documented at the very least. That if someone gives you a date that's just not a valid date, like October 35th, then you should at least say, well, my module will crash or will behave unpredictably. And so for Project 2, your interfaces should appear in two places. First of all, there will be a file called grader that you submit with the project, and that will be worth 10% of your project score. So how you define those interfaces. And that will be what you show to your TA in lab next Tuesday or Wednesday, 1 week from now. So you'll want to prepare this well in advance, but it's okay if changes happen between next week and when you submit the project. You may find once you've implemented stuff that you need to change the interfaces because you weren't communicating enough information. You may tell the TA next week that partner X is going to implement this module and partner Y is going to implement that module, and then when it actually comes time to turn in the project, that will have changed. So you'll be showing one version of the grader file to the TA next week, but then when you submit your project, update it to have the latest information on who actually programmed what and what the interfaces actually turned out to be in the end. Besides your grader file, the other place where these interfaces appear is in the code itself. In front of every method, you put the interface information for that method. So there should be comments in your code for every method that's part of the interface saying what the interface is. Is there any questions on that? Yeah. Class is not the documentation. I'm sorry, can you ask that question again? This is the definition of an interface I've been using, is the prototypes and the unambiguous description of the behavior. So basically the word interface means all of this stuff. That is what an interface is everything in this box. That's how I define it. Does that answer your question? Okay. Yeah. The interfaces appear, should they be exactly the same? I would think so, yeah. I mean, you can have more comments in the code. Your code in general should have more comments than just the interface. It should also have how you implemented things. But, how you implemented things, those comments belong only in your code and not in your interface documentation. Other questions? Yeah. So for your helper functions, you don't generally need as detailed documentation. So you should have some documentation. You should at least say what the helper function does. But the standard is lower. So on Wednesday, we're going to talk about encapsulation and software engineering some more. I'll talk about the list class in Homework 5 and why it was designed the way it was. And then the rest of the semester will be data structures and algorithm analysis.